All right, we're going to take a quick look at lines of constant voltage, or what are called equipotentials, or more general, these are called isolines. And so what we did in this experiment was we set up a battery such that there were 8 volts applied on this big metal electrode over here, and the negative end, or we'll say 0 volts, on the other side. The thing to realize is that, so this electrode, it was connected to the positive terminal of the battery. So you can think of this guy as the positive electrode. We'll put some pluses over here, and then this over here is the negative electrode. What we're going to do here is take a quick look at what these lines mean, these lines of constant voltage, right? Well, one place where you've seen lines of, well, constant anything is on a weather map. And so, well, ever since I was a kid, the weather map pretty much always looks like this. If you draw isolines of various types, we'll draw a few here. So most of the time, the weather map with the isolines looks something like this. These isolines can have different meanings. What they often are lines of constant temperature. So in fact, maybe just for fun here, I'm going to add a little bit more here. We'll do that. So these are often lines of constant temperature, where maybe this is 30, 40, 50 Fahrenheit, 60, and 70. Okay. And so a couple things to think about with this would be like what your experience would be. Say you were driving from Lansing to Knoxville, so that little trip, and what you would experience, versus, let's say you were driving from Nashville up to maybe Yellowstone, okay, and you make that drive, make that trip, and to think about what the experience would be. Well, you notice here you're crossing these isolines. You're going from where the temperature's in the below 30 to a place where it's probably 55. Okay, so the temperature is changing pretty rapidly as you make this drive. You notice this drive here, you're not crossing any of the isolines. It's staying nice and steady. So it's kind of flat. The temperature's staying flat here, where you're climbing like crazy here. Okay. So those are isolines that, if in isotherms in this case, if they're lines of constant temperature. They could also be lines of constant pressure. You could say forget these values here and say you were mapping the pressure. And ever since I was a little kid, like, you know, there's usually a big fat L sitting over Michigan, like a low pressure system. All this horrific weather from Canada likes to come down. And then here over San Diego, great big old H, so that bad weather off the Pacific will come in and decide, nah, I'm not going there. It's a high pressure zone. So these lines could be lines of constant pressure. You could do it that way, but most often on a weather map, they'll maybe do a little of both and put letters to represent pressure, and then they'll draw the lines of constant temperature, right? So another context in which you'd see something like this would be on a hiking map. And so if you look at this, these black lines would be, say, a map of the park, and then the red lines are maybe showing a trail that somebody might hike. Well, if you stop and look at this thing, you know, it's like, well, what do you think this thing over here is? It's probably a mountain, right? These lines are usually showing you lines of constant altitude. They're like contours. And so this thing's probably a mountain. If you want to be snarky, you could say it's like a pit, a conical like pit, but it's probably a mountain. And then this guy over here is probably a lake. And you notice these lines of constant altitude are really far apart out here. So this part of the park would be really, really flat. And so if you look at these trails, right, this one's going and then staying right in between these contour lines, like following around a lake. So you can probably push the baby stroller on this hike. Where this one looks a little more serious, right? You can see that you're having to cross all these contour lines, and you can see that's why maybe there's these switchbacks on the trail. Okay. Now, something to think about before we connect this back to the voltage lines that we drew would be, if you were to, again, let's go with this being a mountain and this being a lake. If you were to set a bowling ball down right here where I'm drawing in blue, let's suppose you set a bowling ball down there. Well, to think about which way it would go. Well, we know ultimately this is the lowest point, the lake, maybe. but the bowling ball is not going to just go straight for the lake. It's not going to head straight here to the left, because then it would be following a contour line. There's no reason for it to move in such a direction that stays at a constant height or elevation. So what this ball is going to do is it's going to want to roll down the mountain. It's going to go this way. It's going to go this way. And we can't really see the contour lines up here, but I'm kind of making this up here that maybe, and it's going to come around like this and then probably roll into the lake there. Right? But notice that the thing took off this way, because what the ball wants to do is roll in the downhill direction, and going straight to the left from the beginning, that's not actually downhill, right? So here it's a little bit easier to see. You know, everybody would say, okay, well, of course it's just going to go straight away from the mountain. So the ball would kind of roll that way. If you put the ball up here, right? Even though the lake's the low point, the ball's not going to go this way, because that would be like climbing up the mountain first and then going back down. Well, it's not going to do that. The ball's just going to kind of roll away like this. Okay, so what we're doing is we're drawing lines along, I guess, the path of steepest descent. If you go that way, you're losing altitude the fastest. In fancy language, by the way, once you get to higher math, this is the direction of what's called the negative gradient, right? It's the path of steepest descent. Also, if we go back to our lines of constant voltage here, you could imagine that I could take, let's say, a positive charge, and just to keep things simple for the moment, let's suppose I take that positive charge and I put it here. So we'll say I've got a little positive charge I can move around, and I'm just going to stick it there. Well, that positive charge clearly is going to be repelled by these positive charges and go toward the negative, because positive charges are attracted toward negative charges. Well, so that positive charge would take off this way, right? Matter of fact, if you put it right next to this thing, it would of course really be repelled. It would go this way, right? If you took a positive charge and you put it here, right? You put the positive charge right here. Its first priority, now, of course, it wants to go to the negative charge eventually, but its first priority here is to get the heck away from this other positive charge. So the repulsion from this nearby positive charge would really dominate. So this thing would really take off this way at first, and then kind of wrap around like this, and then swoop in and come down toward this negative charge. So notice this is very similar to like releasing a bowling ball on that contour map and letting it roll down the hill. That's kind of the same thing. This positive charge would want to roll what toward the negative charge, which is sort of like, metaphorically speaking, downhill for a positive charge. Just for symmetry, we could do the same thing. Suppose we took a positive charge over here. Well, of course, that thing would want to get away from those positive charges, so it would take off, kind of wrap around like this, and come down. The key is, notice that its path of steepest descent is perpendicular to these equipotentials or isolines, right? So we could continue drawing this. If you happen to have a positive charge here, why, it would again want to go toward the negative charge, but it wouldn't go sort of straight diagonal this way. It would want to go like this first and kind of curve around, because it's going to want to, again, kind of roll downhill. Well, so by the time you finish, kind of drawing enough of these where you get to see what the, kind of what the world looks like around these things, what we're drawing here in blue is what's called the electric field. The electric field tells you in which direction a positive charge really wants to go, okay? Couple other little things to notice that we'll build up to later. But if you're out here, of course, the positive charge will want to move toward the negative charge. But you notice these equipotentials are very far apart. So there's not a very big change in voltage if you move here. There still is one. It's still sort of falling as you go this way. So the charge would still be motivated to move, but not as motivated to move as it would be, say, you're here. Notice here a tiny bit of movement really lets you change voltage quickly. In other words, it's like it's very steep here. The voltage is changing very rapidly as you move here, not so rapidly as you move out here. That's very similar to what we saw with this contour map in the state park. If you released a bowling ball here, here's a bowling ball, like, yeah, it would want to go toward the lake, but, not too badly, because locally here it's relatively flat, And so the ball would start to roll, and it would be motivated to go this way, but not as motivated to roll as it is here, where it's very, very steep, right? So these lines of these lines that are along the path of steepest descent, which is the way like a bowling ball would roll, if you do that same sort of thing on a map of voltage or equipotential, what you're actually drawing is the electric field, which is the direction that a positive charge would go.